Hi, welcome back. So we made quite a bit of headway, I think, in terms of trying to get a numerical picture of the boundary layers, right? So we started out with the Navier-Stokes equation, and we came up with a set of equations from using the consideration that is going to be applied to a boundary layer. And we came up with the governing equations for that, for which, and we use knowledge of the physics of the boundary layer as well as the numerical nature of of the equations, so that we can basically get a set of equations which, if we will solve, then it will give us information about a boundary layer. So now let's do that exactly, right? Let's try to get ahead and get a solution for that using those equations. And I think the best place to start is to apply those equations to a flat plate, right? And this basically is essentially was originally done by Blasius in 1908 as part of his PhD thesis, right? So so let's get ahead and see what this is all about. Okay, so the boundary layer equations, right? When we apply for a flat plate, very thin flat plate. So, okay, now the topic as it is now, I would head this. The heading should be something like this. It is basically similarity solution, right, to the boundary layers. Okay. Now, this word similarity is actually a technical word here, so we'll sort of slowly understand what that means, right? So, so essentially what we're doing right now is application. Yeah, so what we're doing is application of the boundary layer equations, right, to a very thin flat plate, isn't it? Flat plate. Okay, and so like I said, this was basically done by Blasius, right, in 1908 in Göttingen. So this is the work which led to Blasius's PhD. Okay. Okay, so let's start with so this is the boundary layer equations now. Okay. These are again the dimensionalized form of the boundary layer equations. Okay, which we finally went back to the dimensional boundary layer equations after we derived the non-dimensional form. Right. So that is boundary layer equations, therefore basically u del x plus v del u del y is equal to nu del u del y2. That's basically the momentum equation, which also accounts for this is momentum equation in the x direction. Yes, basically x direction, but it also takes into account the momentum equation in the y direction because it contains the information about the pressure distribution, right? And then of course this is the continuity. Right? This is subjected to the boundary conditions, okay? Boundary conditions that at y is equal to 0, u is 0 and v is 0. So basically these two are our unknowns, right? And at y far away, u is equal to the free stream. Okay. Now, Right, so so we're going to basically start from here. Now, what's, like I said, the similarity, solution and all that. So let's see what am I talking about exactly. Okay. Now let's look at the boundary layer over a flat plate. And I'm going to do a bit of an exaggerated boundary layer here. Okay. Okay, for some reason I can't draw a straight line anymore with this thing. But anyway, okay, so that's, please consider that to be a straight line. That's hopefully not asking too much. Okay, so this is basically my boundary layer, right? This is my boundary layer, okay? Now, what I'm going to do is look at 4 locations, okay? I'm going to look at 4 locations. So let's do that first. Okay. So say one location is here, another location is here, another location is here, and another location is here. Okay, and I'm also going to draw the velocity profile. Right? I'm going to draw the velocity profile. So, okay. This, right? So, when we do that, okay, and okay. So now let us note these. So this one, okay, is basically, I'm going to call this as x1, okay, this location. This is x2, this is x3, and this is x4. Okay, now this is that. Now, let us, now as you can see, of course, that the boundary, I mean, there are a lot of things to be noticed here. And I think, hopefully, if you're not doing that already, that every time, you see a plot or you see a diagram, begin to take the initiative and begin to or learn to be very attentive and scrutinize things, okay, to pick out inferences. For example, the moment you look at this, what should be the thought which should come to you? First things first, that okay, so we got 4 locations. So how does the velocity profile look like? It seems like the velocity profile at x4, right? It's kind of, the velocity here seems to be at the same height. Say for example, y is much more than what it is here. Okay, and of course, the boundary layer is increasing as we go with x4. So, like we had said earlier, I guess that okay. So therefore, let us say that the boundary layer thickness is delta 1 at this location. So basically, this is delta 1, right? So similarly, this is delta 1. So I'm writing out the coordinates. Okay. Here, so to speak, or I can kind of say that yeah, well, this point is x1 0 actually, and this is my origin. Okay, this is the wrong way to write it, so let me not do that. Okay, I'm going to erase that and say this one is x1 0. Okay, this is x2 0, x3 0, x4 0. So that is this location. This location, okay, and this location is basically this location is x1 delta 1. Okay, this location is x2 delta 2, and this is x3 delta 3, this is x4 delta 4. Okay. So, basically delta 1, delta 2, delta 3, delta 4, that is the boundary layer thicknesses, right, going from here. And of course, this is the distribution of the velocity. And one more thing, I mean, like we've spoken about, of course, is that this is that velocity, and this is of course u infinity, this is u infinity, this is u infinity, this is u infinity, right. Now that's how it is. Okay. So, and of course, what one should understand is that u infinity is a function of x, right. So, you could, although this is u infinity, I could say this is u infinity 1, u infinity 2. So, the u infinity at x1 need not be the same as u infinity at x2. I hope you kind of get that, right. So, u infinity is a function of x, right? That could change, right. Okay. So, kind of think about the possibilities of that as well, and if that's not so, if u infinity is a function of x, then how does the velocity profile look like, and so on and so forth, okay. Okay. Now, in this particular case, right, now let us sort of look at this. So, what I will do is take okay, let us consider these two distances from the x axis. Now, let us consider this location. Okay. Now, this location, if I consider this location, okay, if you look at this and say this location is basically, this height is y1, right, and we will also consider another height, okay, which is y2, and let us say that height is this. Right. So, this height is y2, right. This height is y2. Okay. So, one could I could say this is x2 y1 and this is x2 y2 and so on and so forth. Okay. Now, the question to ask here is that what do you think of the velocity, okay, of the velocity at x1 y1, okay, and the velocity at x2 y1, velocity at x3 y1, velocity at x4 y1. Okay. So, now if you were to look at this, so what I mean by this, so this is x3 y1, this is x3 y2 and x4 y1 and this is x4 y2. Okay. So, what I am trying to look at is that how does the velocity, how does the velocity at x10, okay. So, at the location x1, okay, at a height of y1, how is that related or what, what is the difference or the similarity, if at all anything, between these velocities that at the same height but at different x locations, right. So, you can see it's the same height y1 throughout but different x locations. Right. If I were to look at just the plate, right, at x is equal to 0, then all the velocities are 0, right. All these velocities are 0 when y1 is equal to 0. But when y1 is not 0 and it is a finite value, then what happens to it and what do you think? Right, that how is this the velocity at say y1, how does the velocity at x1 y1, right, compare with velocity at x2 y1, right, at x3 y1 and x4 y1? What do you think, right? How does that even compare? Okay, if you were to pay a little bit of attention to this. Okay. Now, another way of looking at this, right, another way of looking at this is that, well, I mean, yeah, how does this look like? Now, another way of looking at this, which I think I have said this in earlier when we were doing this, is that the delta required or the boundary layer thickness required at x1 is less to reach the free stream velocity compared to the thickness required at x4 to reach the free stream velocity, which means that both at x1 and x4, okay, the boundary layer is such that the velocity does reach the free stream velocity, but at different heights, right. So, that is to sort of give you a hint as to what is going on here, right. So, therefore, that is basically at the edge of the boundary layer, right, meaning that I need a larger height at x4, okay, to get u infinity, and I need a smaller height at x1 to get to u infinity. So, what does that basically tell us in terms of if I were to go between if I were to go along x and different heights along y, then how do the velocities look like, right? Now, if you for example look here, right, now let us just say that the velocity at x1 y1, okay, is not the same as the velocity at x4 y1, at least that much I can say, right. So, this and this are not same, at least they are not same, that much I can say, right, as we go along x. So, therefore, I can probably say, therefore, from that on that account that these two are not same, right. Then, for example, if I look at the velocity, say at the height y2, which is at a larger height of y1, right, which is a larger height of y1, I can probably say that the velocity at this y2 location and x4 location, right. So, that is that is related to the velocity at x1 y1, right, but you have to multiply this velocity by something to get this velocity. Okay. So, let me kind of elaborate on that. So, what I am trying to say here is that, say I take this point, okay, if I take this location at P, right, and I am looking at this location here, which is A, right. So, what I am saying is that the velocity of P, right, which is x4 y2, okay, is similar, okay, to the velocity at A, right, and velocity of P basically if you multiply by say some scaling factor to the velocity at A, right. So, essentially if I were to look at this point P, right. So, P is basically x4 y2, right, and A is x1 y1, right. So, therefore, the velocity at P, right, the velocity at P, okay, is similar is not different, is not much different, is not different from UA because it is shifted, right, along the x and is also shifted along the y. But I can what I am basically trying to say is that if I take this profile here located at x10, if I take this profile, I can actually map this, right. I can take this picture and map this onto here. I can actually map this onto here. So I will need a scaling factor for that, right. So what I am saying is that the velocity profile, okay, at x4, at the location x4 is just a scaled version, right, of the velocity profile at x1. Does that make sense? Okay. I just take so in the behavior as such is similar, right. Behavior as such is similar that it is velocity is 0 at x is equal to at y is equal to 0 and at y is equal to the delta at x4 it is free stream, right. And in between, this is a non-linear change in the velocity, and I am going to say this velocity varies with y, right. So therefore, which is exactly the same picture even at x1, right, except that the values, right, the numbers, okay, at say locations y1, y2, etc. is different, right, because if you see that the same the velocity at the same value of y1, but at x4, right, will be different, right. So if you look at y1 here, right, which is location A, the velocity, the value of u, right, this small u, this is also u, the value of u is different, right, compared to value of u at x4. But basically what we are saying is it's still a horizontal component of velocity, is just you have to multiply, multiply the value of u at x1 by some factor to get this at x4. Right. So, similarly, if I take another height which is not the same as y1 or whatever, is the same thing, right, it's the same thing. So, therefore, for example, if to sort of look at that, so this is the free stream, this is this component, right at the edge of the boundary layer at x4, right, this is u infinity, right. But if I take this velocity profile at x1 and import this and impose this onto the location at x4, I am not going to get that, right. I am not going to get u infinity at delta 1, right. I am not going to do that. So, all I have to do is stretch this out both in the y direction and x direction, so that I get this. So, essentially what I am trying to say here is that velocity profiles at different, okay, this is like a statement, so I am going to write this down, that velocity profiles, right, at different distances right from the leading edge of the flat plate right, are, well, this is a technical term, let me just use, are similar, okay, to each other. This word is very important here, right, this is very important. So, it is similar to each other, okay. So, we are going to use this kind of understanding. So, when I look at the boundary layer, right. So, again, so what the inference which we got just now from this flat plate is that the velocity profile, for example, so this is one bullet, say, okay, and this is the other one, velocity profile at x4, right, Yeah, well, vice versa actually. You could map x4 also onto x1, the velocity profile x4 onto x1, okay. So, this has to be scaled down, right, it has to be scaled up, I mean really that. So, the velocity, let us put it this way, the velocity profiles, right, at x4 and x1, right, can be mapped onto each other using a suitable scaling factor. Using a suitable scaling factor, right. Yeah, so now using scaling factor. So, you have to scale up both the velocity and the y, of course, the corresponding y. So, basically for, so you can say for scaling factor for u, right, and y, for u and y. Okay. Now, yeah, for u and y. Now, let us sort of so let us sort of use the scaling for the let us scale velocities using u infinity and y by delta x. I mean, that's the most intuitive thing to do, I guess. So, let us use scaling factors. For u, let that be u infinity, and for y let that be delta x, right. So, when I say that, so we are going to do a little bit of math and see if we can come up with something interesting. Basically, we are trying to solve the equations, right. Now, so therefore, what we will basically then say, we will define this, right. Because of that, we are going to define this variable eta, right, which is y by delta x, right. We are going to define that value, and we are also going to define this, then u by u infinity, and that is going to be a function of well, that's a function of eta, and this thing, right, this thing, it is independent of x. Now, this thing actually physically, it basically means it's a stream function actually. Okay, what does a stream function do? We can just come to that. You must be aware of that as well, right? Basically, we taking derivatives, we can get the components of velocity back. Okay, all right. So this thing, of course, as you can see, is independent of right, independent of x, right? So now let us sort of look at this. Now, we have looked at how the velocity is looking like, right, as we move along x and so on and so forth. Now, the point is, so therefore, what we basically have said, and learned so far, that now, given that the boundary layer is existing, if I have a fluid, right, if I have, say, if I were to look at this like this, so I have set of fluid particles which comes in, right. So, this is the usual velocity profile that we talk about. So, fluid particles which comes in, right. Now, what will happen? That the fluid particle right at the bottom here, right. So, fluid particle right at the bottom here, that's going to stick to the surface, right. The next ones, right, are slowly, so basically these are going to be shifted up, right. So, if I were to draw a streamline, so it is going to go and then it's going to go like that. So, now so streamline is basically telling you that there is a certain velocity component. That means what? So, therefore, the only way I can, and this is mass, right, this is fluid coming in. So, therefore, I am moving this way, right. I am moving this way, and that is possible because there is a certain exchange of momentum, right, there is certain exchange of momentum. So, there is a certain momentum transport in the y direction, right. So, right. So, basically the you know, the cause of this is the viscosity, right. So therefore, the viscosity, okay, viscosity causes the momentum transport right away from the surface, away from the surface, okay, and the cause of that is viscosity. Now, let this velocity, rather let the velocity which is responsible for transporting, right, the momentum in the y direction be, you know, let's call that uv, right, and of course this is a function of the viscosity and of course the, you know, the amount of boundary layer thickness, you know, that's intuitive, right. So now if I were to sort of say this depends on this, right. So if I look at the dimensions, dimensionally correct, this is a velocity, so units are meters per second. Now if I look at this, right, nu and delta, so I could say that uv could be something like this. This could be a possible function, right. uv depends on nu and delta, and the reason I am writing it that uv is, you know, is something like this is I am just making it dimensionally correct, okay. And delta, of course, this depends on x, I mean that changes, right. Now, we will kind of stop here for this module, you know, and then continue this in the next one where we will, you know, go further down in, you know, getting this solution for thin flat plate, okay. So, see you there. Thank you for now.